Hello and welcome back. We are continuing our discussion of section 1.3, lines and linear functions. Today we're going to focus on the second learning objective here, solve applied problems involving linear functions. So let's skip out. First things first is a kind of convenient way to express the equation of a line, especially initially, just given an initial set of information. This is a pretty convenient format, especially when that information is a slope and a point. Our prior example, you might recall, involved us given 2 points on the line, and that's a common scenario as well. But if we're given a slope and a point, then it turns out that we've got a pretty handy approach. So this is an equation of a line as well. So x sub 0, or physicists might call this x naught. I will probably slip and call it x naught at some point. So x sub 0, y sub 0, x naught, and y naught. These are just coordinates of a point on the line. So what makes these ones different, x and y, are actual variables. So they're left alone as variables to be part of the recipe for our line. And then to fill in the rest of the details, if we're given the slope, we can just dump that in. If we're given x coordinate and y coordinate of a point, we can plug those in as well. This seems a little bit magical, but actually it's kind of familiar. If we did a little bit of algebraic mad science here, if we divided both sides by x minus x naught, then what we get is a big old fraction, y is on top, x is on bottom, equal to m, which is exactly the equation of the slope, even between any 2 points. But what makes a line special, if you recall, is that it has constant slope. So this m will always be the same for points on this line. So we may still end up writing our equations for lines at the very end in our y equals mx plus b format. Some people call that slope-intercept form. But this is a great place to start when what we have is slope and a point to begin with. So what this learning objective was purportedly about, though, was linear functions in applications. So this is what we're going to approach. So we're told that the number of active mosquitoes decreases by 6 mosquitoes for every 1 degree Fahrenheit drop in temperature. There's actually a number of pretty interesting interactions between temperature and insects. One of the well-documented ones has to do with crickets. So the frequency of crickets chirping decreases as the temperature changes. So we're going to look at mosquitoes, though. Okay, so we're told that this rate of decrease. We're also told that at a temperature of 40 degrees Fahrenheit, there are 50 active mosquitoes. Our task is to write an equation for the number of active mosquitoes as a linear function of temperature. And before we actually get to the solution here, I want to take a moment and just kind of break this down a little bit. This equation, this sentence right here has a lot of information about the equation that we're trying to solve. It's got some words that we need to decode, though. So the number of active mosquitoes. Well, okay, so the number of active mosquitoes is a numerical quantity that we're trying to study. And in particular, it's telling us that we're going to write this as a function of something else. So number of active mosquitoes is going to be some input variable, y. And then as a linear function, it tells us the format that this is supposed to go in. So as a linear function of temperature means that it's going to have a pretty familiar format. Linear function tells us that we're going to be looking at something that has the form y equals mx plus b, which is particularly convenient, of course, this section being all about lines, but we can extract this kind of information even when it comes on, say, a test and we don't know what section it's coming from. And then lastly, this final piece of information is basically telling us what is your input. And in this case, temperature is the x value that we're studying. So we'll go on to actually solve this, but it's worthwhile to think about how much information is coded into these statements in English that we can turn into useful mathematics. Okay, so the claim that active mosquitoes decrease, quote, by 6 for every 1 degree drop in temperature basically is slope. It's an indication of slope because for every 1 unit decrease in input, we get a 6 unit decrease in output. So here, 1 unit decrease in input, remember that's our temperature, and then a 6 unit decrease in output, that was number of mosquitoes. So when we look at slope, this is input on bottom, so our input is decreasing by 1, and our output is decreasing by 6. When we divide those two things, we get a positive slope, -6 over -1, which is positive 6, of course. One other piece of information we were handed is that when temperature is 40 degrees, there's 50 active mosquitoes. That's not a rate of change, but it does give us basically a little snapshot. It tells us when the input is 40, again because temperature is our input, then the output, number of active mosquitoes, must be 50. So this is a point on our line, essentially. And now, if you notice, we've got a slope and a point on our line, and point-slope formula is perfect for this situation. So just to identify pieces here, there's our 50 and 40 input, well, output and input respectively, and there's the slope we were handed. So point-slope formula does a very good job of this. Now all that's left to us is to expand and simplify, although it's perfectly worth mentioning that this is a completed equation for the line. This is actually done. There's just a little more combination of like terms that we could stand to do. So with some expansion, 6x and 6 times 40. So on the right side there'd be negative 240, and now you're screaming at me, Mike, there's a typo in your slides. Not at this point anyway. I'm sure it'll come up at some point. But we still have this minus 50 on the left side. So if we add 50 over, we started with negative 240, you add 50 to that, and you get negative 190. So there's the equation for our line. This is kind of the least creative choice that we could have made, x for temperature and y for mosquitoes. So one choice to fancy it up a little bit would be to write in function notation, and maybe we could choose m as a representative, presumably of mosquitoes in this case. If we wanted to go one step further, maybe we could represent our input as t instead of x for temperature. But you know what? We'll take our little steps as we get them. So this either of these formats, y equals 6x minus 190, or with the function notation is an acceptable conclusion. That'll do it for video number 2. Come back for our final learning objective in the next video.